I'm sure you're going to continue to discover in this class, not everything is as easy as it is first introduced. So it sounds great that we can make a direct substitution and evaluate our limits, but that does not always work. So I'm going to give you some strategies to use in the case of where that direct substitution fails. And those strategies often depend on this theorem that I'm going to give you next. And these are about functions that agree at all but one point. So often that means that you've got a graph that behaves just like a line or a parabola, but there's a hole in the graph. Most likely it's due to a denominator equaling zero or some kind of problem with the radical being undefined. And what we can learn from this theorem is that if these two functions, f of x and g of x, agree except for one point. So essentially they're the same graph, they're the same function, except for one point. So that might be in the case of a line. You could think of a line, and then you could think of that exact same line, but it has one hole in it. So they're exactly the same, except for one of the lines is discontinuous and has a hole in it. So if the limit as x approaches c of g of x exists, then the limit as x approaches c of f of x will also exist, and the limit as x approaches c of f of x will equal the limit as x approaches c of g of x. And so what that allows you to do is to do some algebraic strategies that might allow you to get rid of the problem, like having a zero in the denominator and finding the limit of the function that didn't have this problem. One strategy that we are going to use is the cancellation strategy, and we'll factor and cancel and then do our direct substitution. And we want to do this strategy whenever we do the direct substitution and we get 0 over 0. That's an indeterminate form. I want you to look at the spelling of that word indeterminate. And whenever we get that, then direct substitution fails and we have to try a different strategy. We'll be erasing this section and scrolling on up, working on that first example. So in that first example, I have the limit as x approaches -1 of 2x squared minus x minus 3 over x plus 1. I do want you to always start with direct substitution. So your first approach should be to do direct substitution, and you're going to substitute in the -1 for the x. So 2 times -1 squared minus -1 minus 3, your denominator -1 plus 1. So in the numerator, that would be 2 times 1, and then plus 1 and minus 3, and you end up getting 0. In the denominator, you get 0. You have that indeterminate form that I was referring to, in which case you must utilize a different strategy. So the direct substitution method failed, and we need to move on to a different strategy. So this different strategy is we're going to try factoring. If you have a rational expression and one part of it is a polynomial, in this case the numerator, then try factoring. And that would be your second approach. So you've tried direct substitution, it failed. Now we're going to try factoring. We'll do the limit as x approaches -1. Notice that I'm going back to using that notation because I haven't really done the limit yet. Now I had 2x squared minus x minus 3. You can do your factoring any way that you remember how to do it from Algebra 2. I'm hoping that you do remember how to do it. Even if it's nothing more than guessing and checking, my concern is that you can get it to this point. So I want you to factor 2x squared minus x minus 3. That would factor into 2x minus 3 and x plus 1. And if you need a quick review on that, be sure you get in touch with me. And then your denominator is x plus 1. Well, we can simplify by canceling out the x plus 1s, but notice that I have not done the limit yet. I've only done the algebra of factoring, which means I need to continue using my notation that I'm going to do the limit as x approaches -1, but this time I have just 2x minus 3. Now I can substitute in the -1 for the x, 2 times -1 minus 3, and that will give me a limit of -5. And here I do think it's really important that you go back and make a statement what you really did find. You found the limit as x approached -1 of the original problem, 2x squared minus x minus 3 over x plus 1, and that limit turned out to be -5. And I just want to take a minute and show you a graph to maybe explain what was happening here. And for that, I'm going to have to get rid of all my writing, but I still think that's worth it. On this graph, I have shown you what appears to be a line, but actually this is 2x squared minus x minus 3 over x plus 1. And as I scroll and look at what is happening at -1, you will see, if I can hold it steady there, we have a hole in this graph at -1, and that function is indeed undefined. So algebraically, I wasn't able to find the limit by direct substitution because I got a value of undefined. So now, instead of having to make a table and look what's going on to the right, what's happening? Well, that graph's getting closer and closer to a y value of -5, it looks like. What's happening here on the left? Same thing. It's getting closer and closer to -5. Rather than having to look at it using a table or using a graph, we can do the algebra, which is what we did in our problem. We did the algebra, and we found a function that was equivalent. So I want you to notice I'm typing in y equals 2x minus 3. And that was what we found was equivalent. Notice that it looks like the exact same graph, except at -1, now we have the defined point of -1, -5. And so that let me find the limit algebraically without having to see what was happening really close to -1 on either side. I just factored, canceled, found a function that was the same function except for at that one point. And at that one point, I found that the value was -5, and therefore my limit of both of those functions at -1 is negative 5.